Riemann sums come from this idea that we can take a function and we can slice it up into simple geometric shapes like rectangles, and we can sum those rectangles up to approximate the area even of a curve that's smooth and doesn't resemble simple geometric shapes that we studied in elementary geometry. So for this example, what we're going to do is we're going to take the square root of x, and we're only going to look at 0 to 1. So we're going to have this curve here. It goes from 0 to 1. And we want to find the area underneath the curve, essentially. We want to find the area bounded below by the x-axis and above by that curve. So we're not considering this strip here. But we don't have the techniques to do that right now. We have a curve, but nothing from elementary geometry is going to tell us about how to get the area for that curve. So what we can do is we can use concepts we do understand. We do know about rectangles. We know that rectangles have a base and a height. Simple enough. So what we're going to do is we're going to say, okay, well, I'm going to pick several points and I'm going to find the base or the width of the rectangle, and I'm going to use the function value as my height, because that's a pretty good estimation of what the height of that rectangle is the function value. So in this particular case, I know that I'm dealing with the square root of x. So what I'm going to do is I'm going to conveniently pick the input values. I'm going to pick values that are already squared as my input values, so when I run them through the square root, it gets rid of that squared, so my function outputs are very clean. What I'd like to see is function outputs that are like 1 over n, 2 over n, 3 over n, 4 over n, n minus 1 over n. So if n was like 12, this would be 11 over 12, and this would be 12 over 12, which is 1. So what we're going to do is we're going to split it up into some finite number of parts. Let's just say, again, let's say 12. So we would have 112, 212, 312, 412, and so on, all the way up to 1212. Well, to do that, our inputs have to be 1 over 12 squared, 2 over 12 squared, all the way over to 11 over 12 squared, and then 12 over 12 squared. And what you'll notice is that these widths aren't uniform. I drew them kind of poorly, but what you're going to find is that those widths are larger. These should all be increasingly large. But then this one's probably a little too large, but it's okay. We're not trying to draw to scale. We're just drawing to kind of give some basic understanding. So why am I doing this? Well, what I'm going to do is I'm going to say, okay, I'm going to find some sort of endpoints. Now I said 12, but it could be 50, it could be 100, it could be 10 million. And then the function, the value of the function, say the function value at these points, is you remove the squared because we're taking the square root. And of course the square root of 1 is 1. Now you might ask yourself, why don't we have 0 here? Because clearly we start at 0. Well, what we're going to do for this example is we're going to pick the function height at that sort of rightmost value. So we could have picked it at the leftmost value, but we're going to pick it at the rightmost value. But it actually doesn't matter. But by picking it at the rightmost value, we're going to end up stopping at 1, but we don't start at 0. Anyway, that goes all the way to 1. And we can approximate that area by taking each of those rectangles and adding it up. So what we need is that sigma sum that tells me that at each time I'm going to add and add and add and add and add. Again, remember, if you have some experience with programming, this is kind of what you would do with like a for loop. If you were doing a sum plus equals blah blah blah, you loop over. Anyway, you have the function value, which is the height, and then this delta xk is the width. Now the function value of the height is pretty simple. These are the function heights. If we're at the kth version, so the first one is 1 over n, the second one's 2 over n, the third one's 3 over n, so the kth one is k over n, so that tells us about our function heights. But but those delta x's, those widths, aren't as simple. They're not as straightforward. right? They have that variable width. So what we need to do is we need to say, okay, well, the width is just the distance from one x value to the next one. So it's the distance from the x value you're at from the one you were at. In doing that, we say, okay, well, the input that we're plugging in there is some k over n squared, right? Because the output is 1 over n or 2 over n. So the input has to be whatever that number is squared. And then the old one is k minus 1 squared. But notice it's not n minus 1 squared because it's always n. That n is not, we're changing on k, we're not changing on n. So when we do that, when we do a little bit of algebra, we get this 2k minus 1 over n squared. And that tells us the width. Okay, so now we have the function height, which is k over n, and we have the rectangle's width, which is 2k minus 1 over n squared. So that would approximate our height. But let's say we don't want to approximate. You know, this is all good and fine, but what if I wanted it to be a little more precise? I could take more strips and more strips and more strips and more strips and really fill it up. And by doing that, what I'm naturally introducing is the idea of a limit. I'm taking the number of strips and I'm increasing that to infinity. So I'm taking a limit for those number of strips to infinity. So that we approximate the area with this sigma sum, but the actual area happens when we take that same sigma sum, but we instead employ a limit. So if we take the same thing here, and we say, okay, well the function value is k over n, and the width is 2k minus 1 over n squared. Okay, well I've got n and n squared, so I can pull out 1 over n cubed. That leaves this 2k squared minus k. So if you recall from our previous studies on sigma sums and how and the forms for that, you remember that the k squared sum. So first we're going to pull that 1 over n cubed out because we're looping on k, we're not looping on n. So we can pull it all the way out. And then we can use those summation formulas to say, okay, well I know that the k squared sum is n times n plus 1 times 2n plus 1 over 6. And then you have this dangling 2 because you have a coefficient here. And I know that the sum of k from k equals 1 to n is n times n plus 1 over 2. So I have this here and this there. And now I need to do some algebra. Now this one, I actually went ahead and did a lot of it for space saving. So if you do all that together, what you end up with is 4n cubed plus 3n squared minus n over 6. So you're going to get a common denominator of 6. N and n plus 1 are actually already in common here. So you could factor those out, and then you'd have like a 4n plus 2 minus 3, it looks like. And then after that, you'd have to multiply all that stuff out. Anyway, the point being is you end up here, but you have this 1 over n cubed. So let's factor that back in. Now we have 4n cubed plus 3n squared minus n over 6n cubed. So if we're taking the limit to infinity, these have the same degree. They're the same degree polynomial on top and bottom. So as a result, we know that the limit is just the top divided by the bottom, or 4 over 6, which reduces to 2/3. Now that's a lot of work to show that the area here is 2/3. But it stands to reason that it's about 2/3. Why is that? Well, if we were taking the whole square here, it would be width 1 and height 1, which gives us 1 square unit. But we only end up with 2/3 square units. Now this graph probably doesn't do it justice because it's probably not a great estimation, but we should know that no matter what, it should be less than 1, and it should probably be greater than 1/2, because 1/2 would be like the straight line from edge to edge, and this comes kind of over that straight line. So 2/3 is a reasonable answer here. And the idea of the Riemann, this is a lot of work here, no doubt about it, but the idea of the Riemann sum is a necessary step for what we want to get to, because we're moving towards understanding these functions with calculus, and this is kind of the underpinning, and we're going to get to the real sweet stuff, the things that are make our lives a lot easier, but it's always important to come back to this because there will be times when those more simple ways are not applicable and we always have to fall back. So it's important to know the fundamentals.